Good morning, students. Already we have discussed the topic interference. Now today we are going to discuss a numerical based on the topic which we have discussed in our last class. Now let me go through the question what we have written here. In Young's double slit experiment, two slits are separated by 3 mm distance and illuminated by light of wavelength 480 nanometer. The screen is 2 meter from the plane of the slits. Calculate the separation between the 8th bright fringe and the 3rd dark fringe observed with respect to central bright fringe. Now already we have defined the expression for the dark fringe as well as bright fringe. Please check out the discussion, the expression basically, because we are going to use the expression here. Now as per the expression which we have defined in our last class, 8 bright fringe can be defined by capital X suffix 8 lambda capital D by small d. Please check it out. And 3rd dark fringe X suffix 3 is your 5 lambda capital D by 2 small d. So you check the question, equation number 1 and 2 from our previous discussion. Now as per the question, these are the number 1 and number 2 is the distance from the central bright fringe. So as per the question, it is asked to define the separation between these two, x8 and x3. So x8 minus x3, 8 lambda capital D by small d minus 5 lambda capital D by 2d. So if you multiply 2 numerator and denominator on the first term, then it becomes 16 lambda d by small 2d minus 5 lambda capital D by 2 small d. So if you take the difference, it comes out to be your 11 lambda capital D by 2d. Now wavelength is given, lambda is your 8 for 480 nanometer. So 480 into 10 to the power minus 9. And capital D is the separation between the slits and the screen. As per the question, it is your 2 meter. So 2 already substituted. Then 2 small d. Small d is the separation between the two slits. As per the question, it is given 3 mm. So 3 into 10 to the power minus 3 meter. So if you simplify, the result comes out to be your 1760 into 10 to the power minus 6. So if you take the decimal, then it comes out to be your 1.760 into 10 to the power minus 3 meter. So this is the distance between the 8th bright fringe and 3rd dark fringe with respect to the central bright fringe. I think it's simple. Please go through the expression 1 and 2 which we have discussed in our last class. Now the next topic which you are going to define is your diffraction. I think all of you know what is diffraction. Diffraction is nothing but the bending of light. Basically light enters within the geometrical shadow, and this defines the wave nature of light. If light travels in a straight line, then definitely no illumination occurs within the shadow region. But as the illumination occurs within the shadow region, that's why light behaves as a wave. So what we have written, please let me read out. The phenomenon of bending of light around the sharp corners of small obstacles and spreading the light into the geometrical shadow is called diffraction. So you see in this figure, let me try to explain this figure. Now this figure, as is a source, and this is your convex lens. This is your convex lens. So this source is at the focus of this convex lens. So that's why rays goes, and after striking on this lens, it moves parallel. Now these are two gap. This is basically obstacle, and light enters in the shadow region, that is the within the shadow region of the obstacle. And this is also the shadow region. Here is also you will get light, and here is also you will get light. If light travels in a straight line, it goes straight and there is no illumination in the shadow region. But practically illumination occur in the shadow region. That's why you can define that light behaves as a wave. So what happened, as this lens is at the focus of the source, so what will happen, or you can say the source is at the focus of this lens. So rays after refraction passes through parallel through the slit, and the slit has a gap, a small d. AB is the gap through which light is entering. Now this is another lens again. If there is no bending of light, then definitely light moves straight parallel. It strikes on this point of the lens, and it strikes on this point of the lens, and it again further converges at Q. But practically light enters in the shadow region. That's why it says that light is bended, and this bending occurs by an angle theta. So whatever pattern we are getting here, as light is here, definitely light is also here. So you can draw the same pattern considering this geometrical shadow region. So as there is a bending of light, that's why the ray converges at Q dash, and this screen is at the focus of this convex lens. But if there is no bending, then definitely light strikes or converges at the point Q, but practically light converges at Q dash. Similarly, the bending occurs in downward also. Same pattern you will get in downwards. We are trying to discuss the phenomenon by considering the upward bending. Now this separation is, we have considered X, and this slit is of gap small d, and this is the shadow region, and in this shadow region light enters, which define the wave nature of light. Now the slit and the screen is at a distance capital D. Now practically if you consider the extreme two rays, the ray which bends, then you will see that there is a difference in path length. If you consider the light moves from A to Q dash, and that is B to Q dash, you will see that light path length does not remain same. Rather, the path length B and BQ dash is greater than that of A Q dash. So the difference in length is nothing but is your BM. So we have dropped a perpendicular from A, and BM is your extra path that travels by the rays when intersect at Q dash. So the path difference between the extreme two rays is your BM. So if you consider sine theta, then it comes out to your that is BM equal to comes out to be your d sine theta. If you consider this is your 90 degree, so sine theta is if you consider that's a perpendicular by hypotenuse. So perpendicular is your BM and hypotenuse is your small d, so d sine theta. And if you consider another triangle PQQ dash, you can consider sine theta as your tan theta, because theta itself is very small, that's why you can consider sine theta equal to tan theta. So if you consider tan theta, then it comes out to be your QQ dash by PQ. So PQ sine theta equal to QQ dash. So PQ is nothing but is your capital D as per the diagram. And so d sine theta, QQ dash we have considered X. So sine theta equal to X by D. And this is number 2 expression. So expression number 1 is your path difference, and expression number 2 is your sine theta equal to capital X by capital D. And X is the separation between Q and Q dash, and D is the distance between the slits and the screen. Now it is found that when the path difference is a single lambda, then Q dash point is your minimum. That is your first minimum they have considered. Now why the minimum occurs there? It says that what you have to do, if path difference may have any value, is not it. Path difference is BM, so it may have any value. So when the path difference is nothing but the wavelength of the light, then Q dash comes out to be your minimum, and that is your first minimum. Now when path difference is your let me try to explain it here. It says that d sine theta equal to lambda, that is your path difference, as your there BM equal to d sine theta. It is found that Q dash is your minimum. Now the explanation part is that this says that if you consider this is your slit of gap small d as per here, if you consider this one is your the screen is a little bit flickering. Let me try to, I don't know why it is happening. Okay, whatever there. It says that if the path difference, that is your BM is lambda, then Q dash is your minimum, and that is your first minimum. Now the explanation part is your like this. So like this, you have to split the slits in two half. You have to split the slits into two half. If you consider this is your slits, you have to split it into two half, and here is your Q dash. So when ray will come here at Q dash from each of these slits, the path difference is your lambda by 2. Now when the path difference is your lambda by 2, if you consider any ray coming from this half and this half, you have to split the slits into half. So if the ray moves from upper half and strike at Q, and if a ray moves from lower half and strike at Q, then the path difference comes out to be your lambda by 2. Now when the path difference is lambda by 2, then the phase difference is your pi. As per the definition of phase difference is your 2 pi by lambda into path difference, is not it? So path difference lambda by 2, so it comes out phase difference is your pi. Pi is your out of phase, that's why Q point is your minimum. So similarly, if you consider this center is your 2 lambda, again it comes out to be your the point Q dash is your minimum. That is your second minimum, it says. Now the expression part is your what? You have to split the slits in 4 equal parts. So if you split the slits in 4 equal parts, then if you consider any two pair, you will see the path difference is lambda by 2. So as a result, phase difference is your pi. So again minimum you will get. So similarly, if the path difference is your 3 lambda, then again you have to split the slit in 6 equal parts. And for any two pair, the path difference for the point Q dash is your lambda by 2, and ultimately you wish to get minimum. But if the path difference is your 3 lambda by 2, if the path difference is your 3 lambda by 2, so what happened? Because all possible value may come for Bm, is not it, path difference. So if the path difference is your 3 lambda by 2, then you have to split the slits in 3 equal parts. Now for two part, the path difference comes out to be lambda by 2, and ultimately you will get phase difference is your pi. But for another part, there is no corresponding pair, that's why the light enters at Q dash and you will get maximum. Okay, so the minimum comes out when in general path difference is your n lambda and n is your 1, 2, 3. So if n equal to 1, you have to split the slits in 2 equal parts. If n equal to 2, then split the slits in 4 equal parts. If n equal to 3, then split the slits in 6 equal parts. And for any two pair, the path difference when ray reaches at Q dash comes out to be your lambda by 2, and correspondingly phase difference is your pi, and as a result you used to get minimum. Now for maximum part, the n comes out to be your again if you consider 1, 2, 3 like this. So if you consider n equal to 1, then it comes out to be your 3 lambda by 2. So if 3 lambda by 2, the path difference 3 lambda by 2, it means that you have to split the slit in 3 equal parts, and for any two pair the path difference is lambda by 2, but for the third one there is no corresponding pairing, that's why the intensity comes at Q dash and you used to get maximum. So if it is your 2, then it's your 5 lambda by 2. So 5 lambda by 2 means you have to split the slits in 5 equal parts, and for 4 equal parts the phase difference is your pi, but for the fifth one there is a light because there is no corresponding pair. So the explanation part is your what for maximum or for minimum. For minimum, path difference is your n lambda, and the maximum part is your maximum. The path difference is your 2n plus 1 lambda by 2. Now for Q dash is at first minimum. If you consider Q dash is your first minimum, then Q to Q dash gives you half of the width of the central maximum, is not it? And similar pattern occurs in downward also. So if you multiply with 2x, then you will get the width of the central maximum. So if for Q dash is at first minimum, that is n equal to 1, using 1, 2 and 3, it comes out to be your lambda by small d from minimum number 3 equal to sine theta, and sine theta comes out to be your from 2 x by capital D. So x comes out here lambda capital D by small d. Now if you are interested in defining the width of the central maximum, because this Q dash is coming down also, because bending of light occurs due to the slit also in downward, similar pattern as we are getting in upward. So if we multiply by 2 times, that is your 2x is nothing but width of the central maximum. So and my central maximum is your 2 lambda capital D by small d. Now regarding the intensity distribution curve, you will see that in diffraction the intensity decreases. There is a maximum intensity for the maximum, principal maximum, but slowly the intensity decreases with respect to the path difference. But for interference, you will see the intensity is constant throughout, and that is nothing but the distance from the center. The intensity is constant in case of interference, but in case of diffraction, the intensity decreases with respect to the path difference. So please go through this part. This part is very important, and try to find out your doubts. Thank you.